Hello everyone, this is my fifth video in the solution architecture series. In my previous videos, I explained how to functionally decompose a business problem into bounded contexts. Then I explained following a model-driven design for individual bounded context. Though we understand bounded contexts are self-contained, they encapsulate an ubiquitous language. All the model services, etc., they own their own data, but bounded contexts also need to communicate with each other for data and information that they want from each other. In this video, I will explain the different ways in which the components can communicate or integrate. A very popular communication mechanism is APIs, in which client such as frontend or UI sends a request to the backend server and waits for the response. This is synchronous communication. It is simpler, familiar, and very mature in the sense that there are established patterns for security, exception management, layers of API, and so on. While the communication between client and server is termed as north-south, the communication via the APIs among the backend components such as microservices is termed as east-west communication. If the APIs are deployed in different layers and they communicate, then it's still north-west, north-south. Whereas the APIs deployed at the same level, such as within the same Kubernetes cluster, when communicate, it is the east-west traffic. North-south, east-west need different mechanisms for security and monitoring. The API gateway pattern is mostly for north-south, while the service mesh pattern is for the east-west traffic. There can be a scenario in which there are a series of sequence or sequence of API calls or service calls, just as one service calling another service and another service calling the third one. This pattern is a choreography pattern, and there are several disadvantages of the choreography pattern. Multiple point-to-point communication lead to tight coupling and dependency among services. This is difficult to debug, monitor, and test. So there is a pattern called service mesh that can help in terms of monitoring and debugging. There is also challenges with transaction management in terms of this kind of a sequence of services call. And there is a pattern called transaction saga that can help to manage a transaction. Remember, it's an eventual consistency pattern, not an ACID transaction management. Orchestration is an alternative of choreography. In orchestration, a composite service or an orchestrator coordinates the service calls and manages transaction. A client can just call the orchestrator, and orchestrator can call multiple services. Another type of API call can be an asynchronous API call. So before this, we saw all synchronous API calls, which are blocking. So if the backend needs some time for processing, then client remains engaged, waiting for the response. For example, I was solution architect for a customer onboarding in a bank, and when a new customer was created, there were multiple backend processes working off, such as credit bureau check, fraud check, creating new customer in database, etc. The concept of asynchronous API is to avoid the block of flow between two systems. In synchronous communication, for instance, the API call the bank to ask if the customer, let's say actually, in the scenario I mentioned, when we create a new customer, it used to take 4-5 minutes. And for that 4-5 minutes, we can't let the UI blocked. What we did was actually we used to show to customer that yes, you are created, you are successfully onboarded, even though the customer was not actually successful, but everything was not completed. But for customer, we used to show like that. And if in case it's a synchronous communication and from UI, we make a backend call to create a new customer and backend doesn't respond then UI get blocked. For example, whereas in an asynchronous example, an API calls the backend to ask for something, but instead of waiting for the answer, it immediately receives a token that is like an ID of a question without waiting for the actual results. Then this ID can be used to find out the actual information or actual result through a callback or some next call. So in the customer onboarding, when the UI used to call to create a new customer, they were provided with a ID and a request was logged in the database. When a customer was created successfully, the request in the database was updated. The status was updated in the database. Now the UI keeps on polling the database to know that okay, when the customer is successfully created. So UI was polling, and that we call as a client polling pattern. In a client polling, most of the polls are wasted. One way to improve the polling approach would be to use the webhooks. Webhooks are user-defined, that is, the client creates it. These are HTTP callbacks. They are like actually API endpoints. So when the work is completed, the backend service sends a request to the client webhook with the updated status. Compared to polling, there is some added complexity, but the benefit is that in my previous example, I said that UI needs to poll the database. That part is removed now because as soon as the customer is successfully created in the backend will call the UI and update the status. But for that, client needs to host some web point. Client is responsible for keeping the endpoint up, and it may face some hurdles configuring secure access because it needs to permit external requests. Also, because the client provides the web endpoint, you need an explicit agreement on retry policies. To handle webhook failures, you need to define process with an agreed upon expiration window and a number of retries to communicate to the webhook. Many systems such as GitHub and the Stripe have option to configure webhook, which is invoked whenever any code is commit or payment is made. Webhooks may not be suitable in all use cases. There are some ready-made infrastructure and frameworks provided to use the webhook, such as HookTech. Another option is long polling, which is a clever hack for the normal client polling. So long polling may be of 10, 20, or 100 or even more seconds. In long polling, server doesn't close the connection unless it has data to send. Once the server has the data, it sends the data and closes the connection. On client side, you can make a new request after the server responds, or if the connection hang out, then make the new request. Server is fine with the many simultaneous and or pending connections. A practical use case of it is queues. In the case of messaging queues, clients poll the message queue for any new message. There can be an option for long polling where a client can poll for long time, like a 20-second, 100-second. I know I believe in Amazon SQS, it's implemented like that. The client can poll for 20 seconds, and in those 20 seconds, any new message has arrived on the queue, then the client immediately gets that message. There are several ways to implement this kind of long polling, such as wait, asynchronous, redirect, etc. In fact, some languages that are inherently asynchronous, like JavaScript and Go, they make it even easier. But it's still quite a bit of a work to manage the state, etc., on both client and server. Another way of communication is WebSocket. This is again which creates a persistent connection ready for full two-way communication between the client and server. It's fairly lightweight and has very mature libraries in most languages. However, like long polling, this requires another piece of infrastructure that monitors and manages those long-lived connections and processes. WebSockets and similar contracts are wonderful for APIs where real-time is business critical. For example, there is a client which wants to receive regularly updated stock price update. So if they can implement a WebSocket, they can use this pattern, WebSocket pattern. Another pattern is reactive. So in traditional servers, the data would be loaded entirely from the database to the server before any of it was sent back from server to the client. This can be slow. In reactive server, the data will be passed to the client the instant it's available from the server, and it flows out of server. It will flow throughout to the backend application down to the client. This means the client waits less for the first data to appear, and that server doesn't have to store data from the database until all the data is available. Records are processed immediately on being retrieved from the data store and passed on. In some companies and some places, I've seen kind of a bulk or batch API, and typically the REST APIs should be clean, small, and atomic. And API should have one purpose or responsibility, that is bring data from one system or do some kind of a coordination, etc. Sometimes UI may need data from several APIs. For example, the homepage of a banking application data may come from many different systems and corresponding APIs. We can add an orchestrator API that can bring data together from different downstream systems and combine them and send it to the UI in one API call. There can be another scenario in which client may require to call same API with different request contexts. Batch API or bulk API is an interface that allows client to invoke the same API call with different request context multiple times while a single optimized API call. So orchestrator API is one example, and this I'm talking about this. This is another example where client wants to invoke the same API, but each time they want to send a different request context. And maybe there are hundreds of such API calls from the client side. So what we can do is that we don't want client to invoke the same API in bulk in sequence for each request. Instead, what we can give client a facility to put all the requests in one request, one big request, and in one API call, send all the requests. And on the server side, we will handle this. We will get a batch of requests in one call, and then we will break these requests into parallel processing. So we will handle all these requests in parallel on the server side, and then we will combine the response of all those processing and send it back to the client. Another type of bulk API I saw in Salesforce, in which in one request the client was sending different type of operations. So there was some request to create some resource on the server. There was some request to delete the resource on the server. Also a request to get some resource from the server. So everything in one API call. Um, Obviously, actually, this single API has multiple requests, but these requests are directed to different API endpoints. So on the server side, there was a backend who will take this whole request, look for each request is for which API call, and then send it on the backend. It will send it in parallel. So this way, again, actually, we make things parallel processing, also save time. Say we make things parallel on the server side, and we save thus we save time, as well as for client, we make it easier to make multiple requests at the same time. This is another example from Salesforce, where actually we can see the requests include post, put, get, all kind of operations in one REST API calls. On the server side, Salesforce is redirecting different requests to different endpoints. One more pattern is GraphQL. In general, what happens that when UI developers spend more than 50% of the time dealing with the backend endpoint request and response. Any change in the UX needs change in both front end and back end, because the back end might have to add some new fields, and the same API would return some more data in the response. And also many times it happens that API returns a lot of data in the response, and the client or UI doesn't need all the data. Like for example, these are some endpoints for a blogging application. So REST APIs are designed around resources. In most cases, they return a row, a resource, such as a book or an author. And many times client may only need few fields of the book, or only few fields of the author, maybe just the name of the author. For that, and if the client needs few fields of the book and a few fields of the author, then client may have to invoke two APIs and then select those fields which the client needs, and then join them on the client side and present it on the UI. This is not an optimized way. So GraphQL is in which client gets one endpoint that support multiple queries. That is, client can tell that, okay, I want these fields only, and it won't be a new endpoint. So if client just in first time wants the first name of the author and second time wants the last name of the author, so just to return the first name and just to return the last name, there won't be two API endpoints. It should be just one API endpoint that can return different fields. The API on the GraphQL server will fetch the data from one or more and one sources and can return only what client requested. Client specifies what it needs, so avoids overfetching, also underfetching. It's a typical problem of N+1 API calls that can be avoided in the GraphQL. The response includes everything the client needs. It's not like same thing can't be done with the APIs. APIs support query parameters which can be used to achieve the same thing. But I believe there are still some problems with the normal APIs, that API endpoints will not be readable as the number of query parameters become more, and they are from different sources. Also, the API endpoints are defined by the backend developers, not the UI developers. So GraphQL shines at the edge layer of the entire system because, or I might say, the Experience API layer. It's one standard way of implementing Experience API in which queries can be influenced or defined by the UI product teams more easily. Important is client doesn't need to remember multiple endpoints and to change its code when a new version of API is released. All the fields get added or removed to the existing API. It's one API endpoint supporting multiple queries. According to a blog on PayPal, PayPal tried GraphQL many places, and then they came to this conclusion that GraphQL does very well for the orchestration layer. So also a Experience API, like I said, layer. So in the backend, actually, you can still have the normal APIs, but for the user layer, or we can say the business layer, we can use GraphQL. gRPC is another pattern. It's a modern RPC framework, as in all the RPC systems we saw over time. gRPC is based upon the idea of defining a service, specifying the methods that can be called remotely with their parameters and return types. On the server side, the server implements the interfaces and runs a gRPC server to handle the client pods. On the client side, the client has a stub referred to as sometimes it's just called client in some languages, and it provides the same methods at the server. Practically, by default, gRPC uses a file. The format is protocol buffers. The first step when working with protocol buffers is to define the structure for the data you want to serialize in a protocol. It's an ordinary text file with .proto extension. Protocol buffer data is structured as a message, where each message is some small logical record of information containing a series of name-value pairs called the fields, as shown in this example on the screen. Then once you have specified the data structure, you use the protocol buffer compiler, proto-C, to generate data access classes in your preferred languages from your proto definition. The reason to choose gRPC over REST can be to do a contract-driven development in a polyglot environment with a streaming support. gRPC RPC has two types of protocol flows. One is unary, which is a simple request and response, and there is another streaming, which is a non-stop data flow in each direction. Within internal microservices communication, gRPC is a good choice compared to REST. Till now, we spoke only about the request response model, which is considered as tightly coupled in many books. So one application sends a request and wait for the response from the another application. Even though actually asynchronous communication plays some role in keeping things loosely coupled in a distributed architecture, still there is a shared space, or there is a bond between the client and server. Messaging enables distributed communication that is loosely coupled, reliable, and asynchronous. There is a message-oriented middleware is a software or a hardware infrastructure supporting sending and receiving messages between the two systems. So message-oriented middleware comprises a category of inter-application communication software that generally relies on asynchronous message passing. It is not based on request-response architecture. With this system, client makes an API call or service call to the MOM system and sends a message to the destination, which is called a queue in general, and that queue is managed by the MOM. Once client has sent the message, client can continue doing some other work and confident that the MOM provider retains the message until a receiving client retrieves it. Message queues provide a temporary storage when the destination program is busy, the receiver is busy or not connected. In addition, most asynchronous MOM systems provide a persistent storage to back up the message queues. This means that the sender and receiver do not need to connect to the network at the same time. That's why it's asynchronous. The receiver can anytime later may retrieve the message. One other advantage of having a message provider mediate the messaging between client And server is that it adds an administrative interface in between, which we can monitor and tune the performance. But remember, it's still a point-to-point integration because there is one sender, one receiver. So queues store messages until the receiving application is available to receive and process them. Messages in the queues are ordered and time-stamped on arrival. Messages are delivered to the receiver in a pull mode, only delivering messages when requested. The pull operation can be long-lived and only complete once the message is available. If you noted, it's still point-to-point communication integration because it's a single consumer queue in which a message can be consumed exactly once by one consumer or a single consumer. Though message queues support multiple consumer concept, but the idea is one message will only be consumed by one consumer. And the message queue is still a kind of a shared space between a sender and receiver. Both share this message queue. We can still make things more decoupled by using a topic, because in topic a sender sends a message, doesn't know anything about the receiver, and doesn't so sender is sending the message not intended for a particular receiver. Instead, sender doesn't care how many receiver receive the message. It's like a radio, it's like a broadcasting a message. So it's sender publishes a message and all the subscribers receive the message. So we make things even more decoupled with using the topics. Each subscriber or each receiver gets its own copy of the message. So sender doesn't care if the message is handled twice, three times, whatever. But both of these top sense queues and topics can be used in different scenarios depending on the business use case. For example, if we are building a trip management system, so we can use a message queue to make the communication asynchronous. For example, a trip management service can send a message to the message broker, wait for the response, like which driver is available. The requested message will be consumed by the driver service who is listening to the queue, and the driver service produces a message containing a driver details, serialize it into the JSON format, and send a response back on the queue. For example, if we are using RabbitMQ, then there is some direct reply to feature in RabbitMQ, which can be used to send a response on the response queue. And that response will be received by the trip management service, which originally sent the request. Message queue is a shared space here. Theoretically, the communication is asynchronous, but it's still a request response style because trip management is sending a request on one request queue and driver management is sending a message on the response queue. Last 1 decade, since the microservices have become so popular, we are interested in a message-based, event-driven, loosely coupled, eventually consistent architectural approach for communication between services. So we're still actually interested in asynchronous things, but now we want to make things event-driven, and we don't need ACID. We need actually things should be eventually consistent. Using an event-driven, eventually consistent approach, each service publishes an event whenever it updates its data or when something notable happens. For example, customer address changes, and customer will publish an event, customer address changed event, and that event will go on some topic. And there are other services like, for example, order processing service, product service, invoicing service, billing service, who might be interested in this event that whenever customer address changes, inform us. And as soon as they see this event, they consume this event and do whatever is required on their side to handle such an event. If the order service is already processing some order, then they will look for new address and maybe actually place or deliver the order on the new address. So all the services which are interested in events, they subscribe to events. And when they receive an event, they update their data. In another example, if an order service creates an order with a status new and publishes an order created event, the customer service consumes the order created event, reserves credit for the order, publishes a credit reserved event. Order service consumes the credit reserved event and changes the status of order to open. And in this way, we make things event driven. So order service and customer service are communicating with each other, but they are not communicating in the way of request response. Instead, they are communicating through events. They are not waiting for any kind of response, but they are, say, have subscribed to event and they will respond immediately when they will receive the event. So we moved up in this way, we move away from request response style pattern to more event driven systems. This is an example from an NGINX book on microservices that shows different type of communication and interaction styles within the same trip management system. So they took the trip management system, broke it into smaller components, and then they thought about how those different components will communicate with each other. And knowing the different type of integration and communication styles, applied the most suitable communication or integration style wherever possible between any two components. Some places request response, some place publish subscribe, some places notification based. There are scenarios or use cases and different communication style suits in different use cases. APIs may be a preferred way between services with high cohesion, and events will suit services with low cohesion, loosely coupled services. So if you have a order management system and you have a product management system, in the order management system, there can be several subcomponents, and the communication between those communication components can be based on APIs because they are very closely related. There is a high cohesion between them, whereas there is a low cohesion between order management and product management. So when a subsystem from order management communicates with some subsystem of the product management, they can communicate on the basis of events. And sometimes queues will make more sense compared to event driven, but many places our ultimate is to reach event driven, and we should, but not always. And knowing different interaction styles is what the aim of a solution architect is. Thanks for watching this video. If you like the video, please like and subscribe to my channel. Thank you very much.